Now, I hope you're all familiar with Kepler's 3 laws of planetary motion, but just to be sure, here's a quick recap. And what we've seen is very relevant, actually, because ellipses describe the orbits of planets. And Kepler's first law says that explicitly, that planets that orbit the sun, they do it in ellipses with the sun at one of the focus, the prime focus over here, while the other focus is actually empty. And this is, of course, an exaggeration, the thing you can see here, because the Earth's orbit is almost a circle. And it is important just to point out that Kepler's first law is just a consequence of gravity. Now, Kepler's second law is perhaps even more interesting from a physics point of view, because it is a statement of conservation of angular momentum. So physically, you can also write it in sort of this form, but what it tells you, really, in the original formulation of the law, is that the line that essentially is joining the planet to the sun, and in this case, that's joining the planet to the sun, is sweeping equal areas in equal times. The other thing you can obviously conclude is that if the speed is constant, then you must have a circular orbit. And finally, perhaps the law that you're going to use more in a quantitative way is Kepler's third law, or the harmonic law. It's the non-linear relation between the periods of the orbits and the average separation, or the semi-major axis A. P squared, and you can see here, if you don't remember, you should, because you've used it so many times. P squared equals some constant times the semi-major axis. And for the solar system, if we're using periods in years and the average separation, or the semi-major axis in AU, then this constant is 1, and we can just write it as p squared in years equals a to the power of 3 in AU.